Let's do this. Chapter 2. Let's get it underway. Chapter 2 begins with linear and quadratic functions and modeling. That's right, more modeling, word problem type stuff, more modeling. We start by talking about polynomials. Basically, a polynomial is any equation, it's a function that is strung together with pluses and minuses between the terms, and the terms almost all will have variables, but the real important part here is that none of those variables have a negative exponent. It must be non-negative, but it must also be an integer. And when I say non-negative, I mean that can include the power of 0. Like if you just said the number 2, technically you could say that is 2x to the 0 power. So what we're saying is every term has to have pluses and minuses between them, and most of the terms will have x's or y's or whatever. They'll have a variable, and the variable is an integer, not decimal, not fraction, an integer, and it must be non-zero. The biggest exponent is the degree of the polynomial. So you can say it's a 4th degree polynomial, 5th degree polynomial, whatever. It's the biggest exponent. And the number that sits in front of the x with the biggest exponent is called the leading coefficient. That's what all that crud says. So the first thing we're going to do is we're going to look at some examples, and we're going to ask ourselves, is this a polynomial or not? And if it is, we have to say, what is the degree, and what is the leading coefficient? And if it's not a polynomial, we have to say why. Okay? Okay. The first one. Well, let's see. Are there any exponents that are non-integers? No. Are there any exponents that are negative? No. Are all the terms strung together with pluses and minuses? Yes. Well, then this is a polynomial. So we're just going to write yes, because it says, are they polynomials? So yes, this one is. Its degree, I'm going to write deg. Its degree is the largest exponent, degree 3. And its leading coefficient, I'm just going to write leading, is the number that sits in front of the x with the largest exponent, 4. There you go. Very simple. So part B. Is that a polynomial? Why not? The negative exponent is a problem. It's an integer, but it's negative, and that's a no. So no, not a polynomial, negative exponent. Those aren't allowed. I mean, they're allowed, but not in polynomials. C's a little bit tricky. In first period, when I asked the class what they thought, not a single person spoke. So we'll try here. Is it a polynomial, yes or no, class? Yes. Tons of yeses. Very few no's. Yeah, this is not a polynomial. It is not a polynomial, but why? Why?
So the square root is technically to the 1/2 power.
Because the square root is the 1/2 power. Is there a polynomial underneath the square root bar? Absolutely. But that radical stops it from being a polynomial. Now, you cannot, quote unquote, distribute this exponent to the inside because those things on the inside are separated by pluses and minuses. So you can't do that. But all of those objects are still technically affected by that 1/2 power. So we would say, no, this is not a polynomial. Why? And I'm just going to write radical. The radical stops that from being a polynomial. Does that mean I can never have a radical in a polynomial? No, that's not at all what that means. It just means that the radical can't be on any of the x's. I mean, you can have square root of 2. Look, for example, that's still a polynomial because the square root of 2 is a constant. Constants are allowed to have radicals. The variables cannot. So we'll just get rid of that because that's not actually part of the notes, but it's still good video. And then the last one, is it a polynomial? Yes, it is. The problem is it's not in standard form. So let's go ahead and write it in standard form first. Standard form has the biggest exponent variable, I said that weird, the variable with the largest exponent has to be written first. And they're supposed to go in order from big exponent to small exponent. So now it's in standard order. Negative 2x to the fourth plus 15x. So yes, this is a polynomial. It is a degree 4 polynomial, which we can see because it is now written in standard form. And its leading coefficient is negative 2. The negative sign is part of the 2, yes. The symbol that's in front of it, just like the 15x was technically positive, so we could put a plus sign in front of it. I'm sorry?
It would be wrong if you multiplied it by -1.
Yes, you can't just distribute. If you multiply by -1, then you have reflected it over the x-axis. It's no longer the same function. It's still a polynomial, but it's not the same one. Now it's a different one. A little bit of review there for you. What do you guys think? Questions, comments, concerns? That's pretty straightforward. Radicals and negative exponents and fraction exponents, big no-nos on your x's. But all that junk can be done to the numbers. Nobody cares about that. Just can't happen to the exponents. I mean, just can't. Yeah, I said that right. On the variables. So this question is actually an Algebra 1 question. Given 2 coordinates, can you find the equation of a line that goes through them? That's all this is. The difference is it doesn't say x comma y in a set of parentheses. No, instead it says f of -1 equals 2. F of 3 equals -2. Well, the thing inside the parentheses is normally where there's an x, right? Normally it's f of x. So the thing inside the parentheses is your x. So you have the coordinates -1 comma 2 and 3 comma -2. And we just have to find the equation of the line that goes through them. Algebra 1, like a boss. We're going to need our slope. Good old slope formula, m equals y2 minus y1 over x2 minus x1. It doesn't matter which one you call x1, y1 or x2, y2. It doesn't matter. But I'll just do it in the order I wrote them. So -2 minus 2 over 3 minus, ready for this, -1. Turns that negative sign into a plus sign, right? Gives me -4 over +4, which is a slope of -1. Now, well, that's the slope. But I need the equation of the line. So what I'm going to use is point slope form. Because all it requires to write the equation of the line is a point and the slope. Y minus y1 equals m times x minus x1. Like so. And it doesn't matter which point you choose. But I might as well just use the same x1, y1 that I used for the slope. Plug them in, plug them in. Y minus 2 equals -1. I'm not going to write the 1. Times x minus -1, like that. And because we weren't told that we have to put it in slope-intercept form, you could stop working right there. It just says the equation of the line. There you go. It does say a linear function, though, doesn't it? That means it needs to say f of x equals. Okay, fine. So we're going to distribute the negative sign, and then we'll add 2 afterwards. So y minus 2 equals -x minus 1, and then add 2 to both sides. Leaves me with, instead of saying y equals, I'll say f of x. We can squeeze it in over here. Suck it in, function. F of x equals -x plus 1. There it is. Algebra 1. Not bad, right? Yes, sir. Is that stretch or what? Stretch, okay. Nice little review, right? Yeah. Yeah, the slope formula. Well, that was just, I didn't mean to write that. It's bad notes. Because 3 plus 1 is 4, not -4. I'm not sure. Maybe I had like a small stroke or something up here. Good catch, though. Good catch. I mean, I don't know how to edit video, so it's just going to be like that on YouTube. Take that, future comments. All right, kidding. I have comments. I have comments turned off. I don't care about opinions. Alrighty. These 2 questions are all about transformations. We just did transformations, didn't we? This time we're transforming the parent quadratic, we want to know what would have turned the parent quadratic into the g of x that we're given. So we're going to list out the transformations, and then we're going to sketch the graph of g of x using transformation knowledge. Cool beans? Cool beans, great. So I'm looking at A, and I see 3 transformations. I see that negative sign, I see that 1/2 on the front that is on the outside, and I see a +3. That means all 3 of those are y changes. They're all changes on the y's. And well, outside changes do exactly what we think they should do. You know, high velocity, vertical, outside, same. So we're going to describe those transformations following the order of operations. Those 3 transformations are, and I'll just do arrows or something. This minus sign right here, that is reflecting over the x-axis. Reflect over x-axis. And then how about this fuchsia, the 1/2 on the outside? Well, multiplying the outside by 1/2 is doing exactly what it looks like it's doing. It's cutting the y's in half. So this is a vertical shrink of factor 1/2. Hopefully you won't begrudge my shorthand. Vertical shrink, factor 1/2. And last but definitely not least, the +3 at the end. Doing exactly what it looks like it's doing, shift up 3. Man, I don't know about you guys, but I struggle performing those 3 transformations in my mind. That's pretty tough for me to do. So rather than perform those 3 transformations in my mind, what I would do is I would take some coordinates that the parent function there hits, and I would alter those coordinates according to the way that I taught you transformations affect coordinates instead of affecting their graph, and I'll just connect dots. I am going to take 3 really obvious points. I like -2, 4, 2, 4, and 0, 0. Why did I avoid 1, 1? Because that 1/2 on the front, I didn't want to have to plot a decimal, that's why. So I went after the ones with even y values. Let me write those 3 points. Hold on, the board is doing something dumb. Come on back, there we go. Oh, wait, whoa. Oh, technology, God, you're the best. Okay. Let's do our x, y, those 3 points. -2, 4, 0, 0, 2, 4. And because I don't have any more left or right space, what I'll do is I will make my new table, x prime, y prime. I'll do it down here, okay? Guess what? That minus sign and that 1/2 are technically both multiplications on the y values. So rather than multiply by -1 and then multiply by 1/2, why don't I just multiply by -1/2? Which is the same as dividing by -2. So I take my y values and I divide by -2. 4 divided by -2 is -2. 0 divided by -2, wait, whoa, hold on, stop. I forgot to take a step. Nobody's writing in pen, right? Worked ahead of myself. Try again, slow down, take a breath. 4 divided by -2 is -2. And then plus this 3. Got to add 3 at the end. So -2 plus 3 gives me a 1. There we go. Then you take the y value of 0, you divide it by -2, you get back 0, and then you do plus 3. And you know what's great about parabolas? They're symmetric. So I know that's a 1 also without doing any work. And all 3 of those changes were on my x's. I mean, were on my y's. They didn't touch my x's. So the x's are -2, 0, 2 still. Yay! So we're going to plot those 3 dots and connect them. 2, 1. 0, 3. -2, 1. And we have ourselves an upside down short parabola. Woot. Yeah. I like doing transformations that way. It's much easier for me. I can't do all that junk in my head. It's too much work. The next quadratic happens to be written in what we recognize as vertex form. You know, actually A, that was also vertex form. It was just strange. But it was vertex form. Anyway, B is in a vertex form that we recognize. I see 2 outside transformations and 1 inside transformation. So this one will have changes on the x's, whereas the last one didn't. So this 3, because it is a multiplication, we described that first on the outside. That is a vertical stretch. Factor 3. That multiplies my y values by 3. So I'm just going to put in parentheses times 3. And you know what? Let's color code these chunks. Nah, never mind. Let's do it in the same order I did last time. Green, fuchsia. Well, that one, that's an inside change. Hi-oh, horizontal, inside, opposite. So it looks like we're adding 2 to our x's. So we're actually subtracting 2 from our x's. And if you take an x value and subtract 2 from it, it's going to move left on the number line. So this is shifting left 2 units. Shift left 2 units. And you know, I'm slightly better notes. Up here where it says y, where it says times 3, what I meant to do is y times 3. Yeah, take the y value. That didn't work. Take the y value, multiply it by 3. There we go. Because at shift left 2 units, that is take your x's and do x minus 2. You're going to subtract 2 from your x's. And then last is this minus 1. It being an outside change means it's affecting the y's. That's a shift down of 1 unit. It's numeric effect. Take 1 away from your y values. Shift down 1 unit. 1 units. Go home and catch you, you're drunk. And that is take your y values and subtract 1. There. Now for this one, the x coordinates that I'm going to take are -1, 0, and 1. I don't want to use the even ones this time because I don't feel like it. I want smaller numbers because my brain hurts. I want nice, easy math. Again, the only reason on the first one why I didn't use those 3 coordinates that I just chose for part B is because in the first one I saw that 1/2 on the front and I didn't want to have to play with decimals. It's the only reason why I'm choosing the 0, 1, and -1 because there's no fraction. So the original tree, -1, 0, 1, its y values were 1, 0, 1. In red, though, are transformed prime coordinates. Great. I'm going to look over there and I'm going to see that there's only 1 on the x's, and it's the fuchsia one. And it says take 2 away from your x's. So I'm going to look at my x values of -1, 0, and 1, and I'm just going to subtract 2 from each of them. -3, -2, -1. That was easy. And then for the y's, that's green and then orange. Multiply by 3 and subtract 1. Well, 1 times 3 is 3. Minus 1 is 2. Now let's do it with the 0. 0 times 3 is 0. Minus 1 is -1. And parabolas are symmetric, so that has to also be a 2. Plot your dots, connect your dots. And you have shifted left, shifted down, oh, and nice and tall. Ta-da! Yay, transformations. My Algebra 1 students, excuse me, my Algebra 2 students, Freudian slip. My Algebra 2 students took their Chapter 1 test today, which was half transformations. I haven't had the heart to look at the grades yet. I would like to wait until I get home where I can hide if I start to cry. All right, so let's see. Next question. Oh, it's actually not a question. It's a box of information. This box of information is titled vertex form of a quadratic, but it actually covers both standard and vertex forms of a quadratic. Standard form is where it starts right here, ax squared plus bx plus c. Standard form can be written in vertex form, which is what you're seeing right here, by a process known as completing the square, something I know that you all remember and are really good at. Bunch of heads shook no. I didn't think so. It's okay, I got you covered. But yeah, you're going to complete the square on a quadratic that's in standard form to get it into vertex form. When in vertex form, the easiest thing for you to find is the vertex. That's why it's called that. Mathematicians are smart, not very creative though. We like to name our things based off of what they do or what they give us. So this is vertex form. It tells you exactly where the vertex is. The vertex will be at h comma k. That is what makes the inside equal 0, comma that number that's been added or subtracted to the far right, every single time. But if it's not in vertex form, if it's in standard form, then that vertex is, oh, that's right, you got to do a little bit more work for it. So, okay, how do we do it? How do we do it? Well, in standard form, first what you would find is the axis of symmetry. The formula for that is x equals negative b over 2a. The reason why we would find that first is because the axis of symmetry always goes through the vertex. So the axis of symmetry has the exact same x value as that vertex. Now, once you find x equals negative b over 2a, whatever that number is, if you wanted to know what the y value of the vertex is, you would have to plug it in and solve for y. So yeah, finding the vertex is much easier in vertex form. Now, where our quadratics cross the x-axis, zeros, roots, solutions, these are all the same words basically. Well, in vertex form, you would have to set it equal to 0 and solve for x. I think a lot of books call it like solving by extracting roots or something like that. Basically, it just means use PEMDAS in reverse order, get x by itself. If you're still in standard form, though, you do have to use everybody's favorite quadratic formula right there. I was being facetious. I hate the quadratic formula. It's got too much going on. It's too busy. I don't know who you're trying to impress, quadratic formula. And we're just going to do this one example, and that's what we're going to call it for the day. Here we have a quadratic written in standard form. We've been told to use completing the square. That way we could describe this graph. And what we mean by describe is, what's the vertex, what's the axis of symmetry, which way does it point? If you can tell me those things, you're in good shape. So we need to complete the square. The thing about completing the square is it can really only be done if the a term, meaning the term in front of x squared, is 1. Well, this one's not. So what we do is we make it 1. How would I make it 1? Well, no, you're trying to factor. That's intercept form. We'll get there. Now, I need that number in front of x squared to be a 1. It's a 3 right now. So I'd have to, quote unquote, divide by 3, right? Okay, well, I'm going to do a form of division called factoring. But I'm only going to factor this 3 from the first 2 terms. I'm not going to touch that 11 back there. And I left a space there on purpose because we have to find the one magic C value that we could write right there in those parentheses that would make that set of parentheses something we call a perfect square trinomial. A perfect square trinomial is something that will factor into a set of parentheses squared. So that is our goal. We're trying to create a perfect square trinomial. The process of completing the square is literally finding the number that would complete the square. So the first thing we do is we take the b value that's inside the parentheses and we cut it in half. So that's 4 over 2. For us, that's 2. That's not the number. In order to complete the square, you have to take the number that you just found. You switch to red. You have to take the number that you just found and you have to square it. So for us, that's a 2 squared, which is 4. All right, magic C is 4. So we say f of x equals 3, x squared plus 4x plus 4 plus 11. Great. See, if I put a plus 4 there, that set of parentheses will factor into one set of parentheses with an exponent of 2. The problem that we're having here is that I kind of just broke math because I just added a number to one side of the equation. Thomas T., what do you got for me, sir? Normally, you would add it to the other side, right? You can't just add a number to one side of the equation. You got to do it to both sides. Keep the scale balanced, right? But I only want an f of x over there. So pretend you did add it over there. Now what would you do to make sure that f of x is alone? You would subtract it to the other side. The net result would have been like a +4 and -4. That would have given you a 0, right? See, you're allowed to add 0 all you want. You can do that all day long. So I'm not just allowed to add 4. I'm only allowed to add 0. So do I write -4 at the end? No. And here's why. I didn't add 4. It just looks like I did. What did I add? I added 12. You see, if you distribute this 3, that's a +12. So yes, we do have to do it to quote-unquote both sides, but then get the f of x alone. So if I have a +12 going on right there, there has to always also be a -12. If you were to distribute that 3 right now and simplify everything, you would get back the original polynomial, so you know you've actually not changed it at all. It can be factored now. That 3 stays on the front. That set of parentheses looks like this. And guess what number comes after the x? This number, +2. So the b over 2 term will always be inside your parentheses if you complete the square correctly. It'll always be there. And outside, what I have, 11 minus 12? Yeah, that's -1. Boom, there you go. That is the exact same quadratic. That one's in vertex form. Let's describe this quadratic. Its axis of symmetry, I'm too lazy to write all those words, is what? What's its axis of symmetry? Somebody knows half the answer. There it is, x equals -2. You see, the axis of symmetry is a line. And if you just say -2, I don't know if you said a vertical line or a horizontal line. This is an up and down parabola. So its axis of symmetry is an x equals number. X equals -2. Its vertex will be at, what makes the inside equal 0? Come with the number to the far right. And lastly, what I want to know from you is, does this thing point up or down? It points up, but how did we know? Because there's a positive on the front, and positive people smile. This is a parabola. Negative people frown. Oh, if I didn't have a mask on, you'd see me frowning right now. Okay. You know what the shame about this mask is? You guys just don't get to see me frown as much as you normally would. And this opens. Oh, hold on. That says Po. This opens up because the front is positive. And that is going to be a good stopping point for today.